Welcome to the video presentation of Promise. Mobile robots are increasingly used in everyday life to autonomously perform missions such as exploring rooms, delivering goods, or following certain parts of surveillance. The current robotics market is asking for a radical shift in the development of robotic applications, where mission specification is performed by robotic users who are not knowledgeable in programming languages. In this paper, we present a software framework that supports user in mission specification for multi-robot applications. The framework integrates Promise, a language integrated as a DSL that permits the specification of complex missions while being accessible for users and experts not knowledgeable of programming languages. The framework also integrates software components for the automatic mission generation, sending, and interpretation and management. Promise supports the mission specification providing two syntaxes, a textual and a graphical one. In this video, we will make a special emphasis on the graphical one, but we will show how both may be used seamlessly. As the first step for mission specification, we make use of a wizard integrated with Promise, which is used to create the basic structure of the mission, that is, defining the robots and the context of the mission. The mission is then defined by the user by dragging and dropping operators from the given palette, and then configuring them with, for instance, the locations the robot must visit or the action it must perform. Once the user is satisfied with the result, he or she just needs to save and two files will be automatically generated for each robot, containing the mission to be sent and its translation to natural English. This is the definition of the mission we just specified using Promise. It comprises two robots operating collaboratively in the environment shown on the screen. We will now execute the mission in simulation, so the first step is to send the mission to each robot. The root of our mission is the parallel operator, which decomposes the global mission into local robot-specific missions that are executed in parallel. This means that the execution of all the operators associated with one branch of the parallel operator is automatically delegated to a specific robot, as shown in the labels of the edges. The execution of an operator event handler begins with the execution of its default mission, and will not end until this default mission is finished. Concretely, Robot 1 patrols a set of areas in a sequential manner, and Robot 2 waits in L4. If during the execution of this mission the robot senses one of the associated events, depicted as gray ellipses and simulated in this experiment, the operator will trigger the mission linked to that event. In this case, an intruder was detected, and thus the robot will raise an alarm. As soon as the trigger mission is finished, either succeeding or failing, the robot will resume to the default mission of the event handler. Robot 1 now detects a recognizable object, and its mission encodes that the robot must request help from another robot of the team. The execution of this action from Robot 1 triggers the execution of a set of tasks in a sequential manner. First, Robot 2 will visit L2. Once the robot reaches L2, it will grasp the recognizable object. Due to operator fallback, the robot will then attempt to reach Office 1. This operator dictates that if for some reason the robot fails at achieving these tasks, it will try to reach Office 2 instead. In the meanwhile, Robot 1 runs out of battery. Its mission encodes that the robot must visit its charging dock and perform the action charge battery in this case. As shown in the video, we block the way of Robot 2 to Office 1. So after attempting to recalculate its path twice and failing, the robot communicates its failure and tries then to reach Office 2. Robot 1 and 2 succeeded in their event trigger missions and therefore returned to their default missions. Thank you very much for your attention. We hope you have enjoyed this video.